Welcome, dear viewers, back to the channel Rudy's Electronics Labs. And it has been quite for a while. I've been working in Tokyo and traveling around to a couple of other places in the last 2 months. And about to pick up again the channel and post some new videos in the upcoming period, also about the oscilloscope comparison. But today we're going to talk about some instruments that I picked up while I was working for a month or so in Japan. And I did not take a lot of electronics there, but there were a couple of small things that I had to do, and I was in need for a digital multimeter. So I went hunting around a little bit there. And some of you might know Tokyo, and there's this most interesting place which is called Akihabara. And it's a place with quite a history. This is where just after the Second World War, a lot of little shops opened that were selling second-hand tubes, transformers and other components out of old warfare equipment. And people, amateurs, were buying that to build their own radio sets. And this really developed over the many years in a total frenzy, a complete neighborhood with electronics products, later also games and manga. In Akihabara you can find, for example, the largest electronics store in the world, I believe. It's called Yodobashi Akihabara. And just to give you an impression, there you could get lots of different cameras. You can get your regular Sony RX100 or Sony mirrorless cameras. But you also could go there, for example, and get yourself a RED video camera. You could get an Hasselblad or perhaps an Echophase or a Macintosh hi-fi amplifier. Anything you can think of, you'll find it in a place like Yodobashi. But going back now to these old electronic components, there is still this part of this neighborhood, even though every year it's a little bit smaller, where you find a lot of little shops that sell components, that shop specialized in transformers, that shop specialized only in connectors and switches, and there's also shops specialized in measurement and test equipment. And that's of course where I went to try to find a digital voltmeter. And like I said, even every year it gets a little bit small. It's really beautiful to see that this is still somehow alive, that after all these many years there's still this part where all these electronica lovers go to. So I went there looking out for a DMM, and I was looking for something that is small, simple and inexpensive. And I ended up buying a Kyoritsu meter, which is a Japanese meter, of course. You see it over here, and today I'm going to review this. This is really a tiny little meter that's probably best characterized by the fact that it has a current clamp integrated into it and is really designed for kind of higher current type of application, as well as your regular types of AC and DC volt measurements. Now, this Kyocera brand is a Japanese brand. I also had already a couple of other Kyoritsu devices that I already had back home here, and I like them a lot. This is a bit more upmarket. The meter that I bought in Tokyo is actually all the way down at the bottom of the range. I just looked it up, and in Tokyo I paid 9,200 yen. Which equals about 64 euros. And there's several variants, and they go up to 14,500 yen, which is a little bit over 100 euros, I think 101 euros. So these are rather affordable meters, even though they might be a little bit more expensive if you buy them elsewhere in the world. Now, the type of applications that the manufacturer had in mind for these meters are very well shown, I think, by the couple of pictures that we see in the brochure. You'll find things like DC measurements for solar panels, measuring current in switchboard, and servicing a car. And that's really the type of application, I think, where this little meter really comes to life. This is really about measuring larger currents and generic type of AC and DC voltage measurement. This is not the type of meter you'll be looking for if you want to measure very precise currents. If you want to measure precise currents, you can use devices like this here. This is a Tektronix current probe. These are extremely precise, extremely sensitive, high bandwidth, also pretty expensive, separate preamplifier if you want to do very accurate, small measurements, you need totally different type of stuff. This is really type of maintenance stuff, quick problem solving. And having this open current clamp actually is a very nice feature which allows you very quickly to hook into something in a switchboard, in a car battery, and see if something is going on there. Now, actually I ended up buying two different meters. One was intended for myself and one was intended for my son. And I was surprised to find out that these two meters, even if they look almost identical to the outside, they're actually quite different to it. So that's why I'm reviewing these models, trying to give you insight if you're into such a kind of meter, which one you should be getting. Now I can already tell you there are really a number of oddities when it comes to the differences between these two models. And the choices that Kyoritsu made in terms of positioning these two meters are odd, I would say, at the best, and I'm going to talk about that a little bit. And honestly, I get the feeling as if they really had two different design teams working on these two different meters, who both had to produce a meter that fitted exactly in the same housing, but that was about it. So we're going to see a lot of little differences that you won't find in the data sheet or in the manual of these meters. So in this video today I will provide you with a more general introduction. I'll talk a little bit about the specifications and then I'll move on to some real life measurements where I'm going to do both AC type of measurements with pure sine waves, but I also want to move to a little bit different types of waveforms so we can understand a little bit whether having RMS metering on the more expensive of the two models is worth it, makes sense compared to the cheaper model that does not have RMS. So given the category of this meter, I don't think I have to go and get my Keithley 6.5 digit DMM. I mean, the point is here not to show how accurate it is, this type of meter. But I will be using the GW Instack power meter here, and I made a separate video on that one, because then we can investigate a little bit better the voltage and the current readings, and we can also review a little bit the type of waveforms that we are actually measuring. And as sources, I'm going to show them right now. You might not be able to see them when I shoot the rest of this video up in the lab. I'm going to use a variable transformer here, a very old-fashioned device that goes from 0 to 250 volts or so for sine wave signals. And what I'm also going to use here is this actually horrible inverter that you can use in a car, and you connect it to the 12 volts car battery and you get 220 volts. Well, 220 volts, it's not so clean, and that's the whole point. Actually, this device, even if I don't like it, I have to rely on it a couple of times a year when I'm in a situation where I have no power available, and then I would like to know how it's functioning. I actually have to meter the output of this device quite often. So this is a bit of a real life situation that we'll be looking into and see how these two different meters are behaving with that. And I'm going to source this not with a car battery, but I'm going to use a heavyweight power supply that goes all the way, I think, to 20 amps or so. I don't know it on the top of my head, but that I will be using basically to look into some waveforms that are far from perfect, that are certainly not perfect sine waves. So let's go to the lab and let's go and talk about the specs and do some actual real life measurements with these two meters. Okay, there we are. Not in the lab actually, but in another room. It turned out to be incredibly difficult to get a good video of these devices. They're rather reflective. This is the first time I make a video of DMMs, and I tried a little bit around. For what I'm going to do is actually being using this, let me move the camera a little bit up. I'm using this Epson document scanner here, and I think it's a bit of a public secret that this is one of the best webcams that is around. You can put it straight so it looks right into your face. It's super good. Got HDMI out and everything, but right now I'm using it in a way that's supposed to be used, with the lens all the way down, and just looking at my my two different meters. And here we got a picture of the meter. And let me see, I think we can see them fairly well, and the point was also that I wanted to be able to see the display as well, which seems to work. I hope it's looking as good as it looks here on the preview screen that I'm using here. So a quick tour of how the devices look like. You see they're very similar. They're actually very small. I think you can only appreciate how small these are if we would just compare them with a couple of other regular DMMs, which I'm showing here in the picture. After removing the kettles from all of them, you see, so it's really a tiny meter. So how does it physically look like? It is in a cradle. We can take it out of the cradle as the picture you just saw. The electrical leads are permanently fixed to the device. You might like that, you might not like that. What we are having for both devices here is the A version of the device. That's an improved version. Apparently the previous version did not have such a sturdy connection with a stress restraint or so to the body, and that part was improved apparently. So we got the measurement leads over here. They're right on the side. We can take them out. They nicely store in the device, and you can also use that little spot over here basically to put those measurement terminals in and actually use the device basically to touch a electrical contact. And likewise, the power clamp is integrated in device with a permanently fixed wire to it. The other device has exactly the same form factor. The leads are identical. The power clamp is different, as you will see. Let me just put this power clamp back in so we can compare them. So on the cheaper model, we got a power clamp with a manual zero adjustment. On the more expensive model, we got one with a button that automatically zero adjusts. Now, as it turns out, that is a quite important function, because this range here, this potentiometer, goes all the way from like minus 60 amps to plus 60 amps, and it's super difficult to actually set it completely right. I don't really know why there's such a wide range here, but the other one with the button works so much better. So the button behaves more or less like a delta on a regular type of DMM. Okay, so far about the current clamp. Oh yeah, what we also see is that the current clamps are different in size. This one is, let me just take them apart. So we got one current clamp here that is 6 millimeters of diameter. The other is 12 millimeters. You have to take care, it's an open clamp, and that's really attractive. You have to take care, however, that the wire that you're measuring is really properly positioned according to these two indicators that are provided here on the device. Let me see if you can see them well on the screen. Yes, there are two indicators. This you have to take care of, but all well. So this is the physical appearance of the devices. Let's quickly look at the control interface here and turn them on. The first thing you might actually notice is that the screens are different. Actually, they look different. This one is a bit more whitish. The other screen is a bit more yellowish, a bit more greenish, and actually has a little bit less contrast, the more expensive model. These are different screens. We can also see that the information that they can display very shortly if you turn it up is slightly different. Also has to do with the number of counts, which is higher for this model here. What we also note on the control interface is that control surface is that we got the same dial here, but it works slightly different across the models. So in terms of measuring voltages, so alternating currents and direct currents, we got a setting for both of them. All looks great. In both cases, they will do auto ranging, and actually the auto ranges, the ranges for auto ranging are slightly different. And we got here impedance, we got a conductivity tester, and here we got impedance, conductivity tester, but also an LED tester up to 2.7 volts, so your LED will light up and it will show the voltage, and a capacitor tester up to 40 microfarad, if I'm well. Yeah, these are nice functions. I think they're not very critical for the type of application that these people buy this type of meter for. You might have something else at home that can do such a job in a better way. Now, if we now move here basically to the left side of the control scale, and I'll start with a cheaper model. There we got current alternating current and current for direct current. Now that's all great. You have to realize that for current there are no different ranges. So this here is 60 amp range, nothing else. So if you want to measure small currents, like I said before, that's not going to happen on this device. You can also see now, even with nothing attached, no wire here going into the clamp, it's already 3.3 amps. So I will need to get it. So you see here, mate. But the resolution is fairly small, 100 milliamps, and I even have trouble calibrating that. And if I go to the extreme, you will see, well, it's not all the way 60, but plus 20 and minus 20. So it's very hard with this enormous range to get it quite right. The current setting on this device, like I said, we can do with an automatic button. So I'll just press it once and it goes to 0. Oh yeah, that's so much more convenient, as you see here. However, there is something about the current measurement on this device. Actually, you also have two settings here, but this is not alternating current and direct current. No, both of them are current, but this is the 120 amp range and the 60 amp range, which actually ranges fairly close together. Why this has to be two separate ranges almost feels like a kind of afterthought on the device, and you have to switch them here. And AC and DC then has to be selected by the select switch here. I really like this implementation here, where you got like similar type of buttons symmetrically to voltage, a lot over this one here. I find this a little bit confusing here. And then we got frequency measurement. We're going to look at that later a little bit as well, and it both can do frequency measurement from the measurement leads as from the current clamp. I think this shows basically some of the main features of the physical devices as we have them here. I don't think I forgot something. Yeah, both have a hold function right over here, but so this other button, yeah, that might be interesting to say. So here, this button is a selection button in case that we're going from impedance to LED tester to conductivity tester to capacitance and then back. Okay. Over here, this button is similarly switching between impedance and conductivity. However, on all the other ranges, it is manual ranging. And the more expensive model does not have manual ranging. That is a bit odd, I would say. It's almost like the management said, well, you can only have these two buttons, and they had to give up manual ranges because they already had to use that button here for the two different current clamps here. So it's altogether I prefer this user interface over that one, but we'll later see that in a variety of ways this is going to be a more powerful meter here. So let's leave it at that for the first introduction of the device, and let's do some let's hook it up and do some measurements. So now I've hooked up both meters to a little setup here. So what we're doing here is that we got a variable transformer that goes from 0 to 250 volts. The load is a little light bulb over there. It's a purely ohmic load, so like a perfect resistor, we will assume. I've hooked up a power meter over here, so we're going to see a little bit more about the voltage and the current as measured by the power meter, and the two meters here. So I'm first going to do some measurement of AC voltage, alternating current voltage. So let me just move it on here. And what we're seeing here, let me put it 35 volts. I don't know if you can see the light bulb from the camera. It's just out of the picture, I think, but it's just a little bit started to shine here. So what we see here is that both of the devices have fairly accurate readings. The GW Instax says 36.6. Here we also got, well, we got 36.4, 36.7. I don't care so much about, you know, extreme accuracy for this type of devices. This is fine with me. What we do see is that the number of shown digits is different, and this is because this meter, and I'm going to look at the list of specs now, which I'm also going to post, which I worked out for both of these devices. So this is a 3400 count meter, and we're just above 34 volts, so it moved to the next one. And this is a 60,000 count meter. So in many cases we're going to see a bit more, one digit more here. And actually in the most attractive ranges, also if you measure like 5 volts direct current, this one will show you just one digit more than the other one. In the sheet you'll see it worked out exactly when the one is going to show more digits than the other one. Well, obviously we can go here with our transformer all the way to some 220 volts. If I go beyond that point, I think my light bulb is not going to be very friendly to me. It's probably gonna blow. It's yeah, I might do 230, but I rather keep this this light bulb intact. So this all looks fairly well. We can also look at the frequency, and let's move that here. Now, so the interesting thing is a little bit is that the device on the left actually has a pretty wide frequency range. In alternating voltage it goes all the way to 300 kilohertz. In current it goes to 10 kilohertz. The device over here actually has a much more limited range when it comes to power measurement AC, only 400 hertz. No idea why it's so low. However, it does auto ranging much better, or it stays in a smaller range. So we do see the 50 hertz expressed in quite a bit better way, 49.99, than the one over here, where we just see it hidden in the last digit, because it doesn't auto range here in the frequency measurement domain. So actually, if you're interested to see something about the about the frequency of the power grid, I think this one is actually more practical, even though it's much more limited in terms of the maximum frequency it can measure. Okay, I'm going back here to the current measure, to the voltage measurement. What I would now like to do with you is do some current measurement. However, the light bulb I have here actually does not draw that much current at all. It's a mere 250 milliamp. I'm not even sure I'm going to pick that up. Oh, we can try, but I'm not too sure we're going to pick up much in the first place. So this is on alternating current. We're good. This one is on alternating current. So the one over here, okay, it seems pretty much set. Yeah. This low currents, I mean, you can hardly measure. I see going to 1, but that's not really any useful measurement. So yeah, it's not designed for this. I think we shouldn't judge on this. This is really to measure currents into the full amp. So let's try the other one. Let's reset it to 0. Oh, 270 milliamps. Okay, I think that's quite fair. 250. So I got the one wire, I can take the other wire, is going to be a positive value. Yeah, so this one provides us a little bit more resolution so we can actually see it. The other one, let me see again if it's properly set. I think setting of the current amp actually is only necessary for DC current, thinking about it. So, oh yeah, it says so, DC 0 adjust. Because alternating current, it will correct itself every time. So there's nothing to reset. Let me try once more. Yeah, no, this one really cannot measure such small currents. To be able to do this test a little bit, I'll add up a little bit of a larger load. And actually the first thing I add at the hand is a hairdryer. Actually, I took that right away from Japan. This was one that I could switch between 110 and 220 volts. So now it's set at 220, I hope, otherwise I'm going to blow it. Okay, now we should easily be able to bring it to... Okay, now we should see some 5 amps of measurement. So let's see what we get here. 5.3, yeah, 5.6, fine with me. The one over here. Let me see if we get it right. 5.6 and 5.6. So yeah, so that looks fine. So basically it's able to pick up this type of higher currents pretty well. So I think for what the devices were designed to do, this is quite a satisfactory result, taken in mind what we're looking at here. Like I said, this is not a type of meter you would get if you want to do precise milliamp range measurements of or so. Okay, we're moving to the last experiment now, and this is doing measurement with a less than perfect waveform. And again, like I said, I'm going to use this inverter here to be used in a car with a 12 volts car battery and generating 220 volts. This is a horrible device really, but I need to rely on it a couple times a year when I got no other power source available than a car battery. So I would like to know how it measures and how our two DMMs measure the output of that device. Again, it's hooked up here to the power meter. There's a light bulb as a load, and I got the 2 meters over here. Let me turn them on. Going to measure AC voltage. I think all is set. I'm going to use this power supply over here to power the unit, and there we go. Well, the first thing I noticed, and I don't know if you can hear it, but actually this active loudspeaker over here is already starting to give a very nasty type of noise. That's already a warning that we got some really dirty signal going on. There were lots of high harmonics what we're having here. Now, so we see the inverter delivers 228 volts and 263 milliamp is flown to the light bulbs. And what do we see on our 2 meters? The right meter that has True RMS, and actually it measures it quite properly at 229 volts, which is close enough. The left meter is quite a bit off at 215 volts, which must be because it doesn't have True RMS, so it's not able to deal well with waveforms different from being a sine wave. So in that sense, I think the more expensive version of the meter is really worthwhile when you know you might be dealing with signals that are less than a perfect representation of a waveform. And how imperfect is this waveform that we're looking at here today? Well, we can take a closer inspection here on our power meter, and we can get a representation. And let me zoom in the camera a little bit closer here and focus this as well. Yeah, so what we see here is almost a perfect square wave. We got the voltage here in yellow, we got the power flowing here in red, and we got the power in watts as green, and that's always positive because it's the multiplication of the other two I just mentioned. Yeah, so this is really a dirty type of signal, and that explains why the left meter is not dealing particularly well with it. I mean, just try to imagine if these things could be adjusted, and on the basis of just this meter you'll be making adjustments and bringing up to 220 or 230 volts. You will go all the way wrong, and that only because your meter does not have the proper type of measurement to deal with imperfect type of waves. So that's a big plus, I think, for the more expensive version of this meter. So after yesterday's experiments, I felt a little bit unsatisfied about this meter not really picking up the 250 milliamps current or so coming flowing to the light bulb, and so I thought I should do some additional experiments and measurement and try to see in a more systematic way what type of current readings we are getting. So I did further experiments both for AC and DC. So for alternating current, it's the same circuit I used before. You see it here at the top of the screen, which is a variable transformer which has an output of 0 to 250 volts. The power quality meter is going to tell me both the voltage and the actual current flowing, and the power factor is relevant. Then there's going to be loads. Actually, I had multiple loads. Most of them were light bulbs. I went to look around and find a couple of old light bulbs in the house, allowing me for a variety of setting of load. For the very heaviest load, I needed to use a heater. And as you will see in the measurements in a moment, then the power factor is not 1 but a little bit less than perfect, but I don't think it will affect our measurements a lot. And then in the DC scenario, I'll do that using a power supply that goes all the way up to 20 amps, an electronic load, and simply measure the current going over it. And both the power supply and the electronic load actually show already the current flowing. So what were we getting? Let's first look at AC measurements. So what you see here is AC measurement. You see on the leftmost column, you see the actual current flowing, and then we see the current as being shown by the devices. Now, actually, I had 3 of them, 2 of the more affordable one and 1 of the more expensive models. So I used 2 of these copies to see if it could have something to do with a specific copy that I was looking at. And on the right, I'm showing the power factor of the load, but it's always close to 1, so I don't think it should be a concern here. So what do we see here? And I'm looking at currents up to 6 amp. Is that the cheaper models are always significantly off. And what I'm showing here is actually the number of digits that you get to see on the screen. So if you're measuring, if the actual current is 0.7 amps, then it's simply 0.5 shown on the screen of the cheaper meter and 0.70 on the screen of the more expensive meter. So we get 1 digit more to see. So we see the meter is significantly off, all the way to almost 1 amp. Above that, the cheaper meters are still off by some 30% or so. And only when we get to above 4 amps, it gets to what I would call reasonable. At least, yeah, at least less than 10% of inaccuracy. The more expensive meter does a significantly better job here. Note that for this scenario, I didn't have to do any zero adjustment, because with AC the current clamp does not require us to do this. But the results are, I think, very disappointing in a sense, particularly for the cheaper model. So how do they fare when we measure direct current? Well, these are the results. Now I'm measuring up to 19 amps. That's what my setting allowed me to do here. So it seems a bit more accurate, but to be honest, anything below half an amp, the meter was just jumping, or at least the cheaper meters were just jumping up and down by at least 1 digit. So I couldn't really say that there were any kind of stable measurements there going on. So I marked that here in yellow. Then after that, the readings were a little bit more accurate here. And we see that the more expensive meter is fairly accurate here. But in this scenario, I had to do 0 adjustments, and I did that between every single measurement. And the 0 adjustment of the cheaper model is really difficult. I spent really a lot of time trying to tweak around this little adjustment potentiometer, you know, with a fraction of a millimeter, and then it jumped from -5 to minus 0.5 amp to plus 0.7 amp. I think I said it before, but I don't get it why the range of this adjustment parameter goes all the way, I think, from, well, I think it was -20 to +20. It's almost impossible to zero it properly. And even if you manage, it keeps on jumping up or down. So seeing these results really begs the question, is this within the specifications of these devices? So let's look at the data sheet. And what do we see here? Well, this is actually from the data sheet, and I highlighted the part here in this case on direct current. And what we see for the cheaper model, that there's an accuracy of plus and minus 2%, but also an accuracy of 5 digits or 5 counts, I think we should interpret here, as being shown on the screen here. Whichever is biggest of those two. So, I mean, it's not strange in a meter to find this type of specifications on accuracy, but in combination with the fact that there are no different current ranges, there's only the 60 amp or in the other case the selectable 120 amp thing, this really starts to be a problem. And look at the screenshots here below. When I'm actually running 500 milliamps of power through the wire, then you see my 3 meters what I'm getting, 0.3, 0.3 and 0.49. Now the 0.3, what does 0.3 mean? Well, actually it can be -2 all the way to 0.7, that all would be within specs. And even if I measure higher currents, if I would be, for example, measuring, have an actual current of 2 amps, then everything between showing 1.5 and 2.5 still will be within the specifications of the cheaper device. So I think that renders that pretty useless for any measurements of currents that are not at least tenths of amps or so. Yeah, so thinking about that really makes me be disappointed in these devices. I think the more expensive meter still is somehow usable, and we got an inaccuracy of plus or minus 2% and or 8 counts on the display, but since we got 1 count more, I'm a little bit less worried about this one. But still it's not magnificent, because we only have 1 range, or actually 2 ranges, 60 and 120, but they're very close together. Now, before I come to the conclusion of this video, let me also mention that I made an overview of the specifications, both of what I could find in documentation, but also my own observations. And I'll not go through that in all detail, but I'll leave a link below this video so you can look into it yourself. And you'll also find there's a couple of other oddities with these meters. Also in terms of the cheaper model versus the more expensive model, but I'm not going to dwell too long about it right now, and I would like to go to the overall conclusions of this review. Now let's conclude. And honestly, when I started reviewing and recording this review yesterday, I don't think I would have anticipated what my conclusion today is going to be. And that conclusion is that I recommend against buying either of these 2 meters here. As for the least expensive model, I mean, its outstanding feature is supposed to be the current clamp that we got over here, but given the way that it's implemented, given the unacceptable inaccuracies, I would say, and the very painstaking zeroing process for current measurements, this device is not really suitable to measure anything below kind of tenths of amperes, which I think is not really the type of market that people would buy this for. As for the more expensive model, it does a slightly better job at that, but still I don't find it a very convincing meter. Now, if these meters would have had real current ranges, then I think they would have been very attractive as an offering. But as it stands now, I don't think that is really the case. And if you just want to measure voltages and other stuff, I think there's a lot of viable options on the market. You do not necessarily have to look at these models alone. And if you really want to measure tenths of amperes or up to 120 ampere, then I don't really think you're using this type of stuff. You're probably using more sophisticated professional equipment if you really regularly work with that type of currents. So yeah, that's too bad. I would have liked it, you know, to like these Kyoritsu meters, but really not. Better luck perhaps next time.